Behind Claude, ChatGPT, Gemini, or any other breakthrough AI model is one revolutionary idea, that is the transformers. So, if you really understand this one architecture, you'll basically be understanding 90% of how AI models are working these days. In this video, I'll be diving deep into the transformer architecture to understand what is self attention, what is multi head attention, and how these models are able to generate output with such relevant context. So let's get started. Let's first try to understand the history behind how the transformers came into picture. So before transformers, there used to be recurrent neural networks which were good at processing sequential data. It would take in the input, combine it with the previous hidden states to produce the output. Now the limitation with this was difficulty in understanding long-term dependencies. What it means is that as the words grew further apart, it was difficult to establish a relationship between them, grew more and more complex. So that is when the transformers came into picture, and through its self attention layer, it was able to attend every word present in the sentence from every other word directly without having to go sequentially like in RNNs. So let's jump into understanding what is transformer architecture. Transformer architecture basically has two main components. One is the encoder and the other one is the decoder. Encoder is responsible for taking in the input, understanding the input, and feeding that to the decoder, whereas decoder is responsible for writing the output sequence. So I'll be going step by step. First, we'll understand how the encoder processes the input sequence to get a better understanding. And then we'll go to the decoder to understand how it is generating the output text. Okay, so starting with the encoder part, I'm assuming that you already know what are tokens and embeddings. If not, then you please go and watch the video that is linked here where I have talked more about the tokens and embeddings. But just to give a glimpse of that, so tokens are basically larger sentences or sequences of text broken into smaller words, which are then converted into embeddings, which are nothing but vector representation of each word in an n-dimensional vector space, which basically encodes the meaning of those words. So before these embeddings are fed into the encoder, something called as positional encoding is added to these embeddings. Positional encodings basically encode the position related information for each of the word present in the input sequence. Why is this needed is because consider an example like lion attacks man versus man attacks lion. These two sentences have two very different meanings, and in the traditional RNNs, it was taken care automatically because it always processed the input sequences or words sequentially, one word at a time. And when it was processing the current word, it would always look at the previous words to get the context. And since we are not using RNNs in the transformer architecture, so these positional encodings or the position information for each of the word is required. Okay, so after the positional encodings are attached with the embeddings, it is finally fed to the encoder, which basically has the self-attention layer. And this self-attention is the layer where all the contextual understanding happens. So now let's break down what actually happens inside the self-attention. So self-attention breaks down each word into three parts: query, key, and value. So query is what we are searching for, key is label for the relevant information, and value is the actual value of the relevant information. So for example, if a query on YouTube is learn transformers, the key would be the titles of all the relevant videos, and the value will be content of those relevant videos. So if we extend the same example to a text input example, then if you have a text like this, so now if I try to compute the K, Q and V for one of the words, so for example, I'll take the word reel, and the Q for this will be reel The K will be it, posted, maybe, and which are more relevant basically, and perfect, and value will be the same. Similarly, it calculates K, Q, V and values for all of these words and then computes the similarity score between the Q and the K, right? So it will say, let's say, it is strongly related to the word real. So it will have a higher weightage value, let's say, and for the other words like posted or perfect, it will be lower values, and then it will compute the weighted averages by summing all of these up. So it will be like 0.7 into word 1 plus 0.2 into the word plus so on and so forth. So basically, it computes the weighted average from the similarity scores it finds out after finding the K, Q, and V values. Now, the problem with self attention is that because it's calculating the weighted average, the information actually gets blurred. So to solve this problem, instead of using a single self-attention layer, encoder actually uses a multi-head attention, which basically means that there are couple of self-attention layers being used or computed in parallel and not just one. So with multi-head attention, for each of the words, there are multiple Q, K, and V values computed. For example, word 1 will have Q1, Q2, Q3, so on and so forth, K1, K2, K3, and V1, V2, V3. Same with word 2, and so on and so forth. And all of these are fed into different self attention layers, where each layer basically learns a different pattern from all these QKV values. Think of it as passing the input sequence through multiple people who have different expertise. So each layer will basically learn a different pattern. For example, layer 1 can learn, let's say, grammar. Then layer 2 will learn context around these input sequences. Layer 3 will learn something else. So, like that. So after it has learned all of this, it will concatenate all of these results and send it to the feed forward network, which is here. So this feed-forward network is a neural network with hidden layers, which is responsible for processing and transforming the input. So why do we actually need feed-forward network when we already have multi-head attention? Is because multi-head attention has learned the context, but what do we actually do with that context is taken care by the feed-forward network. So it will take the understanding that multi-head attention has built so far around the context and then attend to each of the words individually and form some output from that. So you'll either say that the sentence is positive or negative, or you'll either try to predict something from that. So that is what is taken care by the feed forward network. Okay, so this was the encoder part of it. Now jumping to the decoder side of it. So decoder also has the multi-head attention and the feed-forward network. The difference is that decoder is basically given to the decoder is basically the output that it is generating on the go. That same output is given as the input, and based on that, it keeps on generating the text. It also takes into account input from the encoder, which already has an understanding of the input sequence. So while it is generating the output sequence, it will not only take in the context from the output generated so far, it will also take look back at the input sequence understanding from encoder and use that while generating the output. So for example, the first token that is generated is the start of the sequence token. So I'll just name it as SOS. So first time the input to this encoder is just the start of the sequence, and then it will predict the first token. Let's say it predicts the, and then the input to this decoder becomes this sentence. And then again, it takes a look at the encoder output and tries to predict the next word. The reel was perfect. That was all about the transformer architecture. Just to revise it a bit. So first, the tokens are created from which the embeddings are created for each of these tokens, and then positional encoding is added to preserve the position related information for each of the words. Then that is fed to the encoder, which has self-attention layer. Self-attention basically breaks down each of the word into Q, K, and V value. Means what are we searching for? Key is the label for the relevant information that is needed, and value is the actual value of those relevant information. And once it has that, it will try to compute the weighted averages. It not only has one self attention layer, it has multi head attention, so that there are multiple self attention layers working in parallel, each layer understanding a different aspect of the language or different context from different point of view. Then all of that is fed to the feed forward network, which is a neural network, which transforms or processes the input query. Because by now the context has been understood by multi-head attention, but each word needs to be processed individually also. So that is why we need the feed forward network. Similar things happen on the decoder side as well. It's the difference is just that the input is the output itself, which is being generated by the decoder, and it also takes into account the output from the encoder while it is generating the output sequence.
There are different types of transformer architectures. First one is the encoder only models, second is the decoder only model, and the third is the encoder decoder models. So, now let's take a look at each of these models in detail. So encoder only models are good at understanding input. How it works is that it will take the input sequence and pass it to the bidirectional self attention layer, which understands each of the words by looking at every other words in all the directions. So for example, if there's a sentence like I ate an apple while watching an Apple launch event, it will be able to understand that the first apple referenced in the sentence is the fruit apple, while the second apple referenced in the sentence is related to the company Apple. These models are good at tasks like classification, sentiment analysis, etc. For example, models like BERT. The decoder only models are good at generating text. How they do it is predicting token by token, and while it's predicting a next token, it only takes a look at the previous tokens that it has generated so far. So it has masked multi head attention, masked meaning that the future words are hidden and only the previous words are visible. These models are good at generating code, text completions, etc. Examples of decoder only models include all the famous models that you might be working these days, like Ghibli 5, Claude, Llama, etc. So, encoder decoder models are best for transforming one sequence into another. How it works is that encoder understands the input while decoder generates the output based on encoder's understanding. And this behavior of decoder, where it takes into account the output from encoder, is known as cross attention. An example would be translation tasks or summarization tasks, where for generating the output, an understanding of the input is required. And the models examples include T5, BART. So now let's summarize whatever we learned in this video. So firstly, we went into the different components of the transformer architecture, which is the encoder and the decoders, and then we understood self-attention and multi-head attention and how they establish relationship or context between each of the words with every other word by calculating the similarity scores. Then we went into the feed forward network and understood why feed forward network is needed. Then we went into the different types of transformer architecture models that exists, like the encoder only, decoder only, and encoder decoder models. So if you have any further questions related to this topic, please feel free to drop it in the comment section and I'll try my best to answer it. Also, if you learned something from this video, don't forget to hit like and subscribe to my channel. Thank you.